We report our ongoing development of Palette PrintAR, an augmented reality fluidic design tool for multicolor resin 3D printing. In HCI, there is increasing interest in combining personal fabrication with augmented reality. This includes tools that, as shown to the left, embed AR tags in printed objects, as shown in the middle, allow users to 3D model in mixed reality, and as shown to the right, allow users to interactively control 3D printers in real time. We extend this to resin 3D printing with Palette PrintAR. Here, we use Unity to allow the user to interactively design with the fabrication process. As shown here, the user can model fluidic injection ports for our multicolor resin 3D printing method, simulate in real time with OB fluid, and then print. In this case, we print a distributor network which injects material. The user can then use AR to position objects in the printer for subsequent multicolor resin 3D printing. This ultimately produces objects with rich color material textures not possible with other methods. Here we show results for the case of two resins, blue and white, which the user can inject in opposite corners of the vat. An interface forms in the augmented reality simulation, which is corroborated with real-world experiments as shown here. Afterwards, in the AR application, the user can position objects at the fluid interface or not if desired. Finally, during multi-resin printing, this blue-white interface manifests with the objects that are printed. It is trivial to extend these results to 3 resins using 3 channels on the build platform, as shown here. In this case, the resin distribution is asymmetric. However, objects with similar interfacial appearances are apparent. 4 resins are possible too, using all 4 ports on the platform to make a checkerboard, where parts can be positioned at the interface of 2 or 4 materials. If the user desires to enforce stricter boundaries between resins during printing, they can not only design fluid channels, but also fluidic walls, enforcing barriers between injected resin distributions in the vat. As shown here, for 4 materials, 3 walls separate the materials. The user can then set how much resin is injected into the vat and simulate using OB fluid what the palette of the vat will look like before printing. We corroborate these simulations with real-world experiments as shown here, where the same amount of each of the 4 resins is injected prior to printing. If the user wishes to tune the interface between materials further, they can adjust the quantity of resin that is injected through each of the 4 ports. Here, we are now injecting 40 milliliters of resin through red and green, and only 20 through blue and purple. We perform further real-world experiments to corroborate such results. While the walls continue to enforce the same barriers between materials, the interface at the mixing region is different, leading to objects with variegated color properties. If the user, on the other hand, desires to promote more mixing, they can inject materials very proximate to one another, using blue and red in this case to make purple. Once again, the distributor network is printed, and fluid turbulence causes significant mixing. As before, in AR, the user can position objects in the vat, which then manifest red, blue, and purple, as shown here. This concludes our ongoing work of Palette PrintAR, an augmented reality fluidic design tool for multicolor resin 3D printing.